Happy Friday. So this is our last set of new information for my least favorite unit. Yes, we're almost done. There is warm-up. It's above this line. Actually, it's above this. That's the learning target for today. We're going to learn about drawing conclusions from experiments, and we're also going to learn about other experimental designs. Yesterday we focused on the comparative randomized design. Today we're going to learn a couple others. So I want you to try the warm-up. A biologist would like to determine which of two brands of weed killer is less likely to harm the plants in a garden at the university. Before spraying near the plants, the biologist decides to conduct an experiment using 24 individual plants. Which of the following two plans for randomly assigning the treatments should the biologist use, and why? So plan A, choose the 12 healthiest looking plants, apply brand X weed killer to all 12 of those plants, and apply brand Y weed killer to the remaining. Plan B, choose 12 of the 24 plants at random, apply brand X weed killer to those 12 plants, and brand Y weed killer to the remaining 12 plants. We would want to choose plan B. In plan A, you're taking the healthiest and putting them in one group. So you would assume those would hold up better to weed killer than the unhealthier ones. Where plan B is completely random. You just choose 12 random plants, they go to X, the other 12 go to Y. So, we talked about inference with samples. Now we're going to look at it for experiments. So recall our experiment of online ACT prep class versus the classroom instruction. The results are in the average ACT score for those who took the online prep is 23.2, and the average ACT score for the classroom teacher group is 21. Can we therefore conclude that the online ACT prep class caused better scores? Maybe. Maybe. An observed effect that is so large that it would rarely occur by chance is what is called statistically significant. So we're going to look at why we can only say maybe significant. Sorry. So why we can only say maybe the online prep class caused better scores. And we're going to talk about how we can improve the design of that experiment to account for those different variables. So the first one we're going to look at is called block design. So the counselors at EKHS hypothesized that the online versus classroom results are being greatly affected by the greatest students that were put into each treatment group. They know that juniors generally score better on the ACT than sophomores. They think that the average ACT score for the online class is much higher because there may have been more juniors in that class than in the classroom teacher prep course. How could we argue against it? So one argument is that we used random assignment. In theory, random assignment is supposed to make the groups similar so that we don't have to worry about there being more juniors in the online and more sophomores in the teacher class. Now, let's assume the counselors don't let go of their hypothesis, so they say, hey, let's try this again. So we're going to design a new experiment that takes into account juniors and sophomores. So we had 50 students. And to account for juniors and sophomores, we're going to break them up into juniors and sophomores. And just for the sake of making nice numbers, we're going to say there are 30 juniors and there are 20 sophomores. We're then going to take those juniors and we're going to randomly assign them into the two groups. So group 1 and group 2. 30 students, so there will be 15 in group 1, and there will be 15 in group 2. We have to do the same thing with the sophomores. We're going to use random assignment, break them into two groups. Group 1, 20 kids, so we're going to put 10 in each group. Group 1 is going to get treatment 1, which I'm just going to say is the online. Again, you could say classroom. So, online. Online. I'm running out of room. And then group 2 gets treatment 2, which is the actual teacher. And then we would compare within each group. So we would compare junior to junior. And sophomore to sophomore. Now, in the previous experimental design, the one we just did, the population was split into two groups, juniors and sophomores. Those are called blocks. So this step right here that I did before random assignment, that's called the block step, because I took all the subjects and I broke them into groups that where I know something about them that's similar. So a block is a group of experimental units that are known before the experiment to be similar in some way that is expected to affect the response to the treatments. When the random assignment of experimental units to treatments is carried out separately within each block, we have a randomized block design. So what we did up here, that's randomized block design, because we put them into blocks, so we broke them into similar groups, or I should say groups of similar characteristics, juniors and sophomores, and then from those blocks we randomly assigned. When using, sorry, I feel like I'm going to sneeze. When using a randomized block design, separate conclusions can be made for each block. So that's why we compared the scores for juniors and the scores for sophomores. Don't confuse randomized block design with a stratified random sample. So when selecting a sample for a survey, that's a stratified random sample. But if you're working with an experiment, that's a randomized block design. And then another experimental design that we're going to talk about today is matched pairs. Going back to the ACT prep class, we're going to only focus on juniors. The counselors are now worried that a student's GPA is certainly going to affect their ACT score, and they want to be sure that the different GPAs are being evenly distributed into the two treatment groups. So how can we be sure the GPAs are evenly distributed? We can put the students in order by their GPA and then alternate the groups they go into. And it doesn't matter whether you put the highest GPA at the top of the list or the lowest GPA at the top of the list, as long as they're in order. And then just alternate which group they go into. This is called a match pairs design. And really what we're doing is we're creating blocks of size 2. So we have two students with high GPA. We put one into one group with one treatment. We put the other into the other group with the other treatment. More often, when you're working with the match pairs design, each pair is really just one experimental unit that receives 2 treatments. The order of the treatments can influence the response, so we randomize the order in which the treatments are given. So my example here is I think it's the Pepsi challenge, where you taste Coke and then you taste Pepsi and you say which one tastes better. So that's technically a matched pairs design because there's one experimental unit, the person drinking the soda, and they receive 2 treatments, drinking Pepsi and drinking Coke. And then to make sure that you're not influencing the responses, you should randomize whether each subject drinks first. Oh, excuse me. Scope of inference. What can you conclude in each of the following situations? So the first one says the U.S. Census Bureau carries out a monthly current population survey of about 60,000 households using Table D to select individuals. They find that 12% of the sample are unemployed. So they use Table D, which is a chance process to select who takes the survey. And so we have random sampling, which means we can take this conclusion from our sample and infer it for the population. Two, scientists performed an experiment that randomly assigned 21,000 volunteer subjects to 1 of 2 treatments: sleep deprivation for 1 night or unrestricted sleep. 2 days later, the unrestricted sleep group scored significantly higher on a performance test than the sleep-deprived group. So we have random assignment, which means that we can infer that more sleep, the group that had unrestricted sleep scored significantly higher. Random assignment, it's an experiment, so we can say that more sleep causes higher scores. Alright, so when it comes to inferences about populations, if the individuals were randomly selected, then we can make an inference about the population. So if individuals are randomly selected, and that means we're looking at an observational study. If the individuals were randomly assigned to treatment groups, then we can make an inference about cause and effect. And that's an experiment. When discussing the scope of inference, make sure to always use context. Oops, sorry. Alright, and then one question. So, does talking on a hands-free cell phone distract drivers? Researchers recruit 40 student subjects for an experiment to investigate this question. They have a driving simulator equipped with a hands-free phone for use in the study. So question A, researchers are considering the design shown in the figure below. What type of design is this? So they take 40 students, randomly assign them to the two groups, give them the two treatments, compare their break time. That's just your basic comparative randomized design. B, explain how blocking could be used to improve the design in part A. There's lots of different ways. My first thought was gender. If you blocked on gender, there's a lot of research that shows young males are worse drivers. Their insurance costs are actually much higher than females. So you can block on gender. It doesn't specify age, so you could block by age because you would assume, well, hold on, I'm going to finish writing before I speak. So I was going to say if you block by age because people, you can get your driver's license at 16, so you would assume an 18-year-old who has 2 years of driving experience would probably be a little better than a 16-year-old, somebody who just got their license. But not everybody actually gets their license at 16, so maybe block by years of experience with driving. I'm sure there are others. Those two are the ones that stood out to me the most. And then why is it important to randomly assign the treatments within each book? So that, let's say we're going with gender. So I take my 40 students and I block them by gender. We would still want to use random assignment for the females before putting them into the two treatments, so that we're creating roughly similar groups of females. So we're taking out any other confounding variables, or years of experience would take out any other confounding variables. So RA, important to create roughly equivalent groups within blocks to lessen confounding variables. And that is it for Friday. I'll see you guys on Monday.